Welcome to today's Explainer. I'm absolutely thrilled you're here to dive into this with us. Today, we're exploring what we call the invisible race. We're going to look closely at how entirely invisible factors and particles you can't even see actually dictate the speed of the universe at a microscopic level. It's really cool stuff.
To get started, here's our roadmap for the Explainer. First, welcome to diffusion. Second, visualizing the invisible. Third, the speed factors, and finally, number 4, the great gas race. Let's get right into it.
Okay, let's dive into this. Section 1. Welcome to diffusion.
So how exactly do things mix without us even stirring them? Think about it for a second. If you walk into a completely packed room, your immediate instinct is to spread out, right? You want to find some empty space. Well, beautifully enough, liquids and gases do the exact same thing at a microscopic level.
Which brings us directly to the actual definition of diffusion. It's the process by which different gases or liquids mix entirely due to the random motion of their particles. Because these tiny particles are just constantly buzzing and moving around, they naturally migrate from an area of high concentration, actually think of it like that crowded room where they're packed tightly together, over to an area of low concentration. And they literally do not stop until they are perfectly evenly distributed across all the available space.
All right, moving on to Section 2. Visualizing the invisible.
Now, to really wrap our heads around this, we need some slow-motion visual proof to anchor the concept. So let's look at a classic chemistry observation. Here's the timeline. Step 1, you drop a solid crystal of potassium manganate 7 into a regular beaker of clear water. Step 2, we just observe. After about 15 minutes, you'll start to see this incredibly vibrant purple color slowly seeping out and spreading away from the crystal. Then, step 3, we wait roughly 4 hours for total equilibrium to be reached.
And this brilliantly illustrates the whole process. You start with this highly concentrated crystal just sitting right at the bottom of the beaker. Then, over time, those dense, highly concentrated purple particles are just randomly bumping into each other, constantly moving outward. They migrate away from their dense cluster and straight into the clear water, the low concentration area. Skip ahead 4 hours, and those particles have spread themselves out so perfectly that the entire beaker of water is just one uniform, even purple color.
Honestly, the most mind-blowing takeaway here is this. Absolutely no energy input is required. Nobody is standing over this beaker, vigorously stirring it with a glass rod. This mixing happens completely on its own, 100% driven by the relentless, random motion of the particles themselves. It's pretty amazing.
That brings us to Section 3, the speed factors. First up, let's talk about the physics of temperature. You can think of heat kind of like a power-up. At higher temperatures, particles are infused with way more kinetic energy. They get super energetic, bouncing and zipping around frantically, which naturally means diffusion happens much faster. On the flip side, lower temperatures mean lower kinetic energy. The particles get sluggish and slow down, which directly results in a significantly slower rate of diffusion. Beyond just temperature, the actual physical state of the matter plays a massive role. If you compare gases to liquids, well, it's not even a fair fight. Diffusion happens way faster in gases. Why? Because gas particles are already incredibly spaced out and zipping around far quicker than the slower, much more tightly packed particles you'd find in a liquid.
So the crucial point here is that even if you take two entirely different gases at the exact same temperature, they still won't diffuse at the same rate. The ultimate tiebreaker is their relative molecular mass. Basically, weight dictates the speed limit. Lighter gas particles carry less mass, which means they can travel significantly faster and much further than heavier particles in the exact same amount of time.
Which brings us to our grand finale, Section 4, the Great Gas Race.
Let's meet our competitors, shall we? Coming out of the gates with an incredibly lean relative molecular mass of just 17, we have our first competitor, ammonia, or NH3. You can think of ammonia as the extremely lightweight, highly agile sprinter on our track.
And in the other corner, weighing in with a relative molecular mass of 36.5, literally more than double its opponent, we have hydrogen chloride, or HCl. This is our heavyweight contender. It's mathematically much heavier, which means its particles are destined to move at a far slower pace. So, here is how the race is run. We take a long, clear glass tube. At one end, we insert a piece of cotton wool soaked in a highly concentrated ammonia solution. At the exact same time, on the completely opposite end, we insert cotton wool soaked in concentrated hydrochloric acid. Now these liquids will quickly evaporate into gases and instantly start diffusing down the tube, sprinting right toward one another. When they finally collide, they react to form this highly visible white smoke of ammonium chloride. So, knowing what we now know about molecular mass dictating speed, where exactly in that tube do you think the white smoke is going to form?
Now, what's really interesting about this slide is the definitive visual confirmation of our physics rules. The collision absolutely does not happen in the exact middle. No way. The white smoke forms way over on one side, much, much closer to the heavier hydrogen chloride end. Because ammonia is so much lighter, it just sprinted down that glass tube, covering a vast amount of ground, while the heavier hydrogen chloride was kind of just slowly making its way off the starting line. Lighter mass equals faster diffusion, plain and simple.
You know, this elegant little rule that particles naturally migrate from high to low concentration based on their energy and mass. It governs so much of the world around us. It's the reason you can smell coffee brewing from the next room, and it's literally how oxygen enters your bloodstream. But understanding all of this leaves us with a pretty provocative thought to walk away with. If diffusion is this relentless, natural process driven by endless random motion, and particles are always trying to spread out perfectly evenly, what is eventually stopping the entire universe from just blending into one giant, perfectly even mixture? Think about that the next time you see a drop of food coloring hit a glass of water. Thank you so much for joining me for this explainer. Stay curious and keep learning.